Hello community! Today I explain AI. Yes, the completeness of AI. But to a very special audience. Because I got in my last 4 days 9 emails by students of a class with the task they asked me that if I can explain AI to them. With a specific topic here from data to AI world models. But of course we can. Hey, let's jump into a special edition for schools. Please regard here my ideas as open source, use them, build upon them. And here we go. Now I understand, because if I ask Claude 3 Opus here for a summary for a school class and explain artificial intelligence and a targeted and educated audience, my goodness, this is so boring. And if I go to ChatGPT 4 Turbo, my goodness, even more boring, just technical mumbo. So let's be brilliant. Let's use our human brain for this. What do we have? We have a lot of data. We have a lot of books. We have a lot of information. And we have an AI model. We want to have an AI model, so we have to build an AI model. Now, what is the task of the AI model? Simply to reproduce the data. But it is not just a string copy. It is a little bit more creative. So we learn now in this AI model specific data distributions, I show you in a minute, by adjusting here the neural network weight tensors that live inside here an AI model, normally a transformer model. However, the data are not just human data. We have to tokenize those data. We have to tokenize the human language. And either a word is a token or a subword is a token, a byte per encoding. We have more than 20 different tokenization systems for the human language to make it more easy to calculate for the mathematical operation. And then we understand with AI, we work with probabilities of specific distributions. And yes, this is something beautiful about mathematics and statistics. So let me give you an example. If I have a sentence, today is a sunny day, or today is a rainy day, today is a stormy day, today is a cold day, and you want to reproduce this here as an AI model, you ask, hey, can I have a little bit more information? Maybe the sentence after this or the sentence before this, so I can understand what is the context that we are talking about. So the machine needs more surrounding data right next to it, and therefore we talk about here a context length. We want a real big context length of 10 sentences, maybe 100 sentences, to be absolutely clear what we are talking about here. The semantic content that we want to reproduce and generate. Therefore, we talk about generative AI system. Now, as I told you, statistic here, we have a beautiful distribution, a classical distribution. And if we train now on some data, or we have some sentences, we see there's a high distribution, a high probability here that if I have the term sunny, and I have a day here, and then a beautiful here, and the weather here, and a little bit further down here, the probability I have happy, and maybe I have ice cream. So you see, those kind of go together if I have a sentence with, what a beautiful sunny day. Now, we can do the same here for rainy. Rainy day, dreadful, cold weather. Maybe instead of an ice cream, we go for a warm cup of tea. You get the idea. So we have statistical data, and we have different data distribution that we are working with. And there is a beautiful mechanism for connecting here all the different words or subwords or tokens here over this beautiful context length that we have a look at with our AI model. And this mechanism will be called self-attention. And self-attention is our workhorse here that we use here in the transformer architecture. Now, if you say attention, what does it mean? It is very easy. You look at a specific sequence of sentences, and then you ask for each word in each and every sentence, how much attention should I give to each other word starting from my word? When we do now a mathematical calculation of the highest probability for the next word that the AI model will create. And we talk here about an autoregressive system. Now, a very simple idea. We have here a sequence of words. Like, today is a beautiful, and now the AI model has to find the next token, or we say predict the next token. And we hope that today is a beautiful day. Could be beautiful second, a beautiful month, a beautiful moment. We have just that the model is able to calculate here with a high probability, given the data sets that we use here, what would be here, given this book here, the next token. So you see, we just predict future values like our next token in a sequence here by using here some previous outcomes within the same sentence. So the model learns from the data. Beautiful. If we look a little bit more at the mathematical side, we say now here, if I have a sentence about sunny, I know what is my distribution. Or if it's about rainy, I see. Those would be my next word tokens. So this is how an AI system, an autoregressive system works. We simply compare probabilities of distribution. That's it. That's all there is to AI models. And if we predict the next token, have you seen it? Let's go back. Predict the next token. Then we have here the next token. And the next job is here to predict again the next token. So if we build a story, if we build sentences, it always predicts the next token based on the data here. And this is what we call a training data set. Beautiful. Now you see, the AI model does know nothing from itself. We have to train our AI model on a specific data set. This means calculating the highest probability for the next word in an autoregressive system is based on what is now the data in this book. What are the sentences, the sequence of words in the sentences in these chapters of this book? Now, the training we have today, 3 steps. At first, we do a very general pre-training. It takes a long time, and we have here a training data set of about 10 to 100 trillion token for our big, large language models like ChatGPT. Then we want to have a fine-tuning for one specific task, like, for example, question and answer, or a summarization task. There is a special fine-tuning that we apply to our AI model in step number 2. And then A, B, C. Now the last step is we want, with a DPO alignment, that our model is nice, is friendly. You know, these beautiful models that we know from ChatGPT. Now the training time that we use, training time can vary from 6 months on huge computer center somewhere in the United States or somewhere in Europe or somewhere in Asia, up to just an hour if we have a rather small model. So let's talk about model sizes, because model comes in different sizes. And the model size parameter is the free trainable parameter in our transformer architecture that defines here the ability of the model to learn more complex structures. Now, beginning here in March 2024, if you invest about $5,000, you can buy you a computer, maybe an Apple with a unified memory here, that you can work and maybe you can fine-tune 7B systems, so 7 billion free trainable parameter systems. If you invest double, let's say €10,000 when you're a student or whatever, you can handle systems that are up to 13 billion free trainable parameter. So you see this you can do if you buy multiple GPUs, if you buy specific advanced Apple SoCs, but you have here a limitation simply because it's so complicated to calculate this in the area of 7B to 13B. Now, if you are a company and you say, hey, I want to invest $1 to $2 million for a GPU node of 8 GPUs from NVIDIA, an old A100, for example, you can then, if you invest this money, have a fine-tuning, maybe a training of 100 billion free trainable parameter models itself. And if you're a real big company like, I don't know, Microsoft or Google, you are here investment about 500 million plus, and then you can build models of up to 1 trillion free trainable parameters. So this gives you an idea what you have to invest and the size of the model that you will see here all over the internet. Now, to make it a little bit easier to work here with, for example, the 7B model, we can reduce the mathematical precision with what we record data. Normally, we would be in a floating point 16-bit precision, but we can reduce here the precision how we record singular data here down to a 4-bit quantization. Now, there is currently a threshold of about 4-bit for the quantization. If you go down lower, you will lose performance of your system. But there's also another mathematical trick. You just do not go for the numerical mathematical precision of your data, but you can also hear a parameter efficient fine-tuning mechanism where you have a low rank adaptation when you do matrix multiplication or tensor multiplication in specific mathematical spaces. And therefore, there's a beautiful methodology if you do fine-tuning that the complexity for your computer, for your GPU, is reduced with a parameter-efficient fine-tuning optimization. So you see, with this new methods, we can bring the complexity even to little personal computer, to little AI machines. Now, the next step was simply that now, looking now at the data, the training data set, we have all the language data, and now we simply add a two-dimensional image data set. You know, whenever you take a photo, we have here what we call a pixel. This is here the minimal size of the information in a two-dimensional image data set. Now we combine this different ways. One way would be here a mixture of expert model, where we have now a tokenization. Now, the language tokenization, we already had a look at this. The word, the subword, byte pair encoding, or whatever you choose. And then for image, we have also a tokenization. Either you go here with the object in the image, or you go with the sub-objects. In the classical way, we went with a patch, with a 16 x 16 pixel patch, or 32 x 32 pixel patch, or you go to the pure pixel level. The pixel space in itself is really complex to compute and takes a long time to compute. Therefore, we go here to patches. Patches are arrays of 16 x 16 pixels or 32 x 32 pixels, and it is much easier to operate on patches. Of course, you also can go to sub-objects, which make it even simpler to do the calculations. Or we combine language data with some Python code sequences or with some C++ programming languages. This is rather easy. We need at first the language training because it should, for example, be able to understand if I have here somewhere a comment in English, that it understands here what is the comment in English. And then, of course, you want to have here the Python code structure. So you just have to increase your available vocabulary, since we have a lot of commands here from the code itself. But otherwise, this is a rather simple way to build here some code machines. Now here we have two options. Either you go with a proprietary machine, like a GitHub Copilot machine, where the AI is more or less giving you code suggestions that you as a developer or as a coder then use in your program. Or if you do not want to pay here global corporation, there's something called an open source, a free version that is available to the public, to everybody free of charge, like StarCoder 2. If you see this today on the internet, now you know what it is. However, there is a little bit of a problem with cybersecurity, but as always, you have to be cautious where you import your data and if the data are maybe infected with some cybersecurity objects. So we have now a dataset where we have again the human language and videos, pure video data. As simple as this. And if you want to know more about this, I have here two videos for you that explain how is it possible that we can have a text-to-video AI machine. And if you have heard the name Sora, this is one of the machine text-to-video from a company called OpenAI. And if you want to see more about the technology background and how to update here, the technology Sora is now 1 year old. There's a regular technology update, so you have to stay up to date. Given now that, as I told you, the transformer architecture of our AI machine is improving, people are researching this, and now currently we have a context length, you remember, of about 1 million token, and in the next month we will reach 10 million token. This is performed by a very special attention mechanism that University of Berkeley calls a ring attention mechanism, and it is implemented in a ring of machine. So we achieve this extreme context length by simply pure compute power. But since we are almost always cloud-based, there are real attractive financial possibilities to rent a GPU in the cloud or a cluster of GPU in the cloud, given your specific task. Now, with this long context length, it is easy to integrate now image and video data. And as you know, since those training here of our AI models take a long time, always there are some new data generated. Every day new data are published on the internet. With this beautiful ring attention, we have now the option here also to include external data. And this system is called retrieval augmented generation here, where we integrate new data, let's say from the internet or from specific databases, SQL, NoSQL, or we do a similarity search in a mathematically optimized vector space, where all our data are encoded in a vector embedding. And with this new data, we can build a better large language model prompt that includes now the new data. And with this new data in our prompt, we now utilize something beautiful that each transformer-based LLM has. And this is a function we can call in-context learning. So if we provide in the prompt to the AI machine 1, 2, or 3 examples what we want the machine to do, the machine in general is able to perform this in-context learning here without changing the tensor weights in its internal structure. So we do not have to have any training of our LLM, but this is happening, if you want, on the fly during inference. Beautiful. Now, last month something happened. Remember, we started out with our large language model, then we added two-dimensional images, so we are now with vision language model. You know, for example, GPT-4 Turbo, or you know, for example, Claude 3 Opus. But also we can extend this to vision language action models that we use when we have to control a robot that moves in a room. This is called a VLA, or simply you know the name robotics. And this is here with increasing complexity, because if we have now action to decide if the robot moves in a three-dimensional space, you can imagine that this gets mathematically more and more complicated to compute. But there's a complete new trend happening. And you heard this, and in one of your emails you said, what is a world model in AI? I have a particular specific video where I show you that the idea is implemented in Sora and in Video JPA. These are things where, let's say, computer scientists say, hey, if I have a recording of something, and I have a recording of the same event from a different angle, or I have a recording from top down. So if I have the same event happening and I record it from different perspectives, can I build from the video data here a real three-dimensional world model? This becomes interesting if we go now from a pure two-dimensional image-based sequence that build our current video, if we want now to move out of the two-dimensional space in a pure three-dimensional space and understand the dynamics in this space. So if you hear world model, this would be here the latest development. We use video data and try to understand what is happening in real time in the real world. But this uses a lot of compute power. Of course, what would be the logical next step, but has not been implemented yet, is to give those AI machines now the power to calculate here, let's say with a code interpreter in Python or any other programming language here, real trajectories. If you throw a ball in the reality and you want to build a world model, so when you record here the scene with different cameras, that you know if you predict the next frame and the next frame of your video where the ball will be, given the laws of nature, given how a trajectory on the planet Earth is, this would need to be calculated here with real physical models, and therefore you need, for example, Python or C++ to do the calculation of the formulas. This is currently missing, and this step will be the next step here for world models. But we also have here a glimpse even to the next step after that, world models that are interactive. That you know with your PlayStation or whatever you have, if you push here and button up, down, left, right, jump, whatever, you can then move in three-dimensional, let's call it game worlds, and you can look around here with your goggles and you really have an immersive feeling that you are playing here on, I don't know, a particular planet somewhere in the outer solar system, and there you have your adventures. This is what here Google DeepMind called Genie. This is a system here that learns here in particular from a lot of video games, a lot of video scenes. It learns what are possible action within the video, and it tries to build an interactive game environment for you. And there you have it. This is it. But let me tell you, currently we are facing as an AI community two big problems. The first is, takes a lot of energy for the companies like Amazon or Google or Microsoft to run those very big, very expensive models. A lot of energy, a lot of water for the cooling of the machines. So those massive cloud compute centers that are distributed all over our globe on all continents, they use a lot of water, energy. And what we want is here to make here the system faster, use less energy. And one interesting idea is here from Quark AI here, the LPU inference chip, for example. Another possible solution to save here our environmental resources is that now those global corporations start to build their own smaller but less intelligent AI models, arguing that a lot of people, 90% of the people, have only simple tasks. They do not need those complex AI machines. And there's currently the trend that you offer here, the public here, smaller machines that took here a lot of knowledge from the big brother machines, but are faster, cheaper to run here operationally. But of course, since all those corporations are profit-oriented, the prices for the consumers stay high, and those companies currently make a lot of profit. So you see, this is here. We have to be careful about our natural resources on our planet, that we do not waste them. The second problem is somehow connected with that. As I told you, we have data, and the data train here our AI models. Now, our AI models are now so advanced that they can give you also an answer if you have a question, but they can also produce data, and they can produce complete data sets. So now we use here our models to generate new data sets. The problem is that those data are not human-generated data, but synthetic data generated by the machine. And if the machine makes one mistake in generating here a data set of 100,000 lines, and maybe there's only one little mistake somewhere in the line 5,600, this mistake is in the data. And you know what's happening now. If we have, for example, on a cybersecurity threat, we have some infected rack system, the infection here, the cybersecurity problem, will now transport it to all interconnected services. In addition, you know, because the data are the foundation of all the intelligence in our AI systems, people now and corporations use more and more synthetic data because they are cheaper to generate. There's no human oversight that you can say, hey, I hire 100 or 1,000 people and they constantly look at my data, validate my data, sort out, filter out data that are bad data. So those synthetic data now, again, in the original cycle, start to train our AI models, but now we have synthetic AI models. So we have now synthetic models that reproduce synthetic data, and you see now the problem that we have in a circle, because if we use the synthetic models as our original models, or just extract here we carve out some smaller models, and then the cycle continues and it continues, and the synthetic data got magnified and magnified. And whatever happens here, or is a data that we don't want the machine to behave or give an answer that we do not want in this synthetic cycle, this becomes really problematic. And it is caused because the human data becomes so valuable, and human audited data are so expensive now. They are up to a multiple of 100 compared to the price you can have if you just buy machine-generated synthetic data. So you see, the future, those global corporations look out for human-generated data. They talk to newspapers, they talk to different platforms on the internet. They are all looking for human data because it is easy to generate synthetic data, but the value is in the human data. And of course, if you have now in this closed loop of synthetic data generation and synthetic model generation that generate again synthetic data, if you have somewhere a cybersecurity threat or a cyber worm, you know this is multiplied x times. So let me leave you here with that we have to be careful. Because on the one side, we have now AI machines and AI operating systems that were created with synthetic data, with a lot of synthetic data, with an extreme amount of synthetic data. But maybe we as human, we don't want here the behavior that the synthetic data show us. And to have the energy to have all of those AI systems on our globe, maybe we have to generate more and more energy. And if we have to burn here fossil fuels like coal, we pollute the environment and we get here an environmental problem in the long term on our planet. So you see, this is also kind of a vicious cycle. Now, with AI and AI machines, the extreme power that those AI machines need, so guess it is also up to the next generation to find here a good solution to those problems. AI is nothing that is happening to you. You decide when you want to use artificial intelligence, when you want to apply those AI systems to your actual problems. But it is completely up to you how the future of AI will look and how we have to use resources from our planet for this beautiful new AI world.